This section explains why all of classical mechanics collapses into a single object. Mechanics reduces to the action, which is stationary on the physical path. Nastase's opening chapter is bookkeeping around that one fact. The Lagrangian is only a representative. Adding any total time derivative, df by dt, leaves the Euler-Lagrange equations untouched, so the physics lives in the action and the Lagrangian merely names it. Everything that follows is a re-coordinatization of that same stationary point. Constraints, the Legendre transform to the Hamiltonian, canonical transformations, Poisson brackets, Hamilton-Jacobi. Hamilton-Jacobi is the limiting case of the series, a chart in which every new coordinate is conserved and the motion becomes trivial. The chapter exists so that one index can later go continuous. The discrete family of coordinates q sub k, for k running from 1 to n, becomes a field h of x. Field theory is this same formalism with the label k replaced by a space-time point. This section explains where symmetry actually lives in a classical theory. Symmetry is a property of the action. The Lagrangian is the natural place to look for it and the wrong one. And that gap is the chapter's whole reason to exist. Nastase's second worked example, Plantin theory, will not have. At a total derivative to the Lagrangian, and the Lagrangian visibly breaks under Q maps to minus Q, while the action survives because the boundary term integrates away. Since the action is what the path integral weights, a symmetry that the equations of motion enjoy but the action does not, is a symmetry the quantum theory will not have. Everything downstream is bookkeeping for that claim. A group says what sameness means. A representation says how it acts on this particular theory's variables. A Lie algebra is the group read infinitesimally, where invariance becomes checkable term by term. This section explains how the rotation group and SU2 both fall out of a single demand. Fix a quadratic form. Demand that a linear map preserve it, and the group falls out of the condition itself. Orthogonality comes from preserving the squared length of the difference between two position vectors, r sub I minus r sub j. Unitarity comes from preserving the squared modulus of a complex vector q. In both cases, a determinate restriction follows, discarding parity and keeping only what connects continuously to the identity and keeping only what connects continuously to the identity. Nastase's chapter is the calibration instance for Chapter 2's abstract machinery. Every notion defined there gets exactly one worked realization here. What the chapter plans for the rest of the book is the gap between algebra and group. The Lie algebras SU2 and SO3 carry the same commutation relations, yet minus the identity belongs to SU2 and not to SO3, so one winds twice around the other. The bracket knows only the neighborhood of the identity. Topology is what exponentiation cannot see. This section explains the role special relativity plays in this book. It installs a selection rule. Fix the group that preserves the space-time interval, delta S squared. That group is O13, the metric preserving conjugate of O4. Every subsequent object in the book must then declare how it transforms under it. Objects that transform correctly are tensors. Objects that do not are outside physics. Nastase gives his own compression of this. Physical quantities transform covariantly, that is, they form tensors. The chapter's payoff is that the electric field E and the magnetic field B stop being two fields and become the single antisymmetric object F mu nu, forced by nothing but index bookkeeping. Symmetry first, content second. This ordering is what the field theory chapters inherit. This section explains what changes when mechanics becomes field theory and why electromagnetism is the demonstration case. A field is the same variational principle with a bigger index set. Replace the world line label tau by every point of spacetime, and the particle coordinate x to the mu, a function of tau, becomes a sub mu, a function of x to the rho, 1 degree of freedom per point, with spatial position demoted from a variable to an index. Everything else survives intact. The action stays the integral over d4x of the Lagrangian density. The variation still integrates by parts. Euler and Lagrange's equation returns unchanged, but now holding pointwise. Electromagnetism is the chapter's proof that this costs nothing. Half of Maxwell's equations turn out to be an identity, solved once and for all by writing f sub mu nu as the partial derivative with respect to mu of a sub nu minus the partial derivative with respect to nu of a sub mu. The other half fall out of a single scalar minus 1/4 times f sub mu nu f sub mu. Field theory is mechanics with a continuum of labels. This part explains why the scalar field is the poorest object in field theory, and why that poverty is exactly what makes it useful. A scalar field is the field with nothing to transform, no index, no rotation under boosts, just a number pinned to each point of space-time. Nastase's chapter earns its place by showing that this poverty is the point. Discretize space, and the free scalar Lagrangian becomes an infinite chain of coupled harmonic oscillators, the gradient term turning into the spring, the square of the difference between neighboring displacements, Q, at site A. Everything after that is decoration of that skeleton. Change the potential, and you get sine Gordon or the Higgs double well. Change the kinetic term, and you get dBi, or a metric in field space. The chapter is the book's cheapest laboratory, 1 degree of freedom per point, on which every later structure can be rehearsed before vector and tensor fields complicate it. Symmetry breaking, solitons, topology. This section explains what remains of field theory once the requirement of relativity is dropped. What makes a field theory is a field over space and time, and action and boundary conditions. Relativity is an extra constraint that one family of these theories happens to carry. Remove the Lorentz constraint, and the actual machinery survives intact, and it keeps producing physics. 2 consequences follow. The Schrödinger wave function falls out of the massive complex scalar in the limit where the speed of light goes to infinity. Water waves, solitons, and growing interfaces fall out of the same formalism with no quantum mechanics anywhere in it. The chapter's function in the book's arc is to detach field theory from relativistic field theory, before Part 2 builds solitons in earnest. It also plants the Korteweg de Vries soliton, Scott Russell's canal wave, as the physical ancestor of every soliton to come. This section explains how discretization defines a field rather than approximating one, and how integrability survives the passage to the continuum. Discretization is a definition of field, not an approximation of one. Hand a chain of sites, a variable, spin, position, anything at all, then send the spacing to 0 at fixed length. The free massless scalar falls out of nearest neighbor, Heisenberg coupling with no field ever postulated. The chapter is the book's bridge from particles to fields, and it buys a second thing on the way across. Integrability survives the limit. A finite system with as many conserved quantities as degrees of freedom expressed as a lax pair, where the time derivative of L equals the commutator of L with M, sends its conserved traces, the trace of L to the nth power, upward. Solvability is a property of the discrete skeleton that the continuum inherits. This section explains why the matrix omega carries the entire chapter. Once phase space stops being the pair Q and P and becomes a single vector eta carrying an antisymmetric form, Hamilton's equations collapse to one line, eta dot equals omega, which is membership in the real symplectic group in 2n. The partial derivative of H with respect to eta, the Poisson bracket, becomes the partial derivative of F transposed times omega times the partial derivative of G. Canonical transformation stops being a definition and becomes a theorem. The condition is m times omega times m transposed equals omega, which is membership in the real. Fields cost nothing beyond two substitutions. The index sum is replaced by an integral over d cubed x, and the partial derivative is replaced by the functional derivative delta. The discretization of chapter 6 does the translating, and the three-dimensional delta function of x minus x prime replaces the Kronecker delta with indices j and k. Every structural equation is the Kronecker delta with indices j and k. What the chapter is for? The bracket becomes the generator of motion, taking over the role the Lagrangian held. That is what gives the solitons and charges of the later chapters an algebra to live in. This section makes one claim. Feynman diagrams are what iteration looks like when you draw it, and nothing about them requires quantum mechanics. Take a nonlinear field equation with a source and invert the linear part. What you get back is a fixed point equation rather than a solution, because phi sits on both sides. Substituting the previous order back into itself generates the whole perturbative series, and each substitution is a picture, propagator lines, source crosses, and vertices where n legs meet. The chapter's thesis is that this whole apparatus is a mathematical trick for solving nonlinear equations needing no quantum reference at all. The quantum theory merely adds loops to what is here strictly trees. Classical means the field is intense, many quanta, so the classical response is the limit the diagrams already describe. This part explains how the list of possible fields is fixed before any field is written down. Field content is a census taken over the symmetry group of space-time, and this chapter runs it. The algebra SO 3,1 factors into two commuting copies of SU2, so every Lorentz representation carries two spins, J tensor J prime. Wigner supplies the pivot. The governing group is Poincare, and a particle's own momentum selects the subgroup that fixes it, the little group, which in the massive case is SU2 diagonal. Its irreducible representations are exactly what a single field may be. Ordinary addition of angular momenta then does all the work. Zero tensor. 0 is the scalar, 1/2 tensor 0 and 0 tensor 1/2 are the two Weyl spinors, 1/2 tensor 1/2 is the vector, and 1 tensor 1 is the graviton. Every field the book later quantizes was already enumerated here. This section explains why the Pauli exclusion principle belongs to the theory of rotations rather than to the theory of electrons. The Pauli exclusion principle is a theorem about rotation. Nastasse's chapter earns its place in the book by showing that a field's behavior under exchange of two identical quanta is already fixed by how the field transforms under the Lorentz group. Spin dictates statistics with no independent postulate. The compression is this. Relativistic invariance plus positivity admits exactly one consistent quantization per spin parity. Positivity means positivity of energy for bosons and positivity of the norm for fermions. Half-integer spin forced into commutators, or integer spin forced into anti-commutators, breaks causality. Fields at space-like separation fail to commute. Statistics is where symmetry and locality intersect. This section explains where gauge invariance actually comes from and what killing it produces. Gauge invariance is the price of writing the field strength as a derivative. Write F equals dA. The Bianchi identity, dF equals 0, forces the potential A to exist, and A is then determined only up to the exterior derivative of a scalar lambda, since D applied twice gives 0. That single line generates everything else in the chapter. The Maxwell action is 1/2 the integral of the norm squared of the two-form F. The equation of motion is d star F equals 0. The whole apparatus is index-free, so nothing inside it knows that the form degree, P equals 1. Raise the rank and antisymmetric tensor gauge fields come out for free. Mass breaks the structure. A term of the form m squared times a sub mu times a upper mu names a explicitly rather than only through its derivative, so the redundancy dies and the Lorentz gauge dies with it. What remains is the Proca field. This section explains why the energy-momentum tensor exists and what it replaces. Energy density was never a Lorentz invariant quantity, so the chapter stops protecting it and lets it become a component instead. Take translation invariance seriously in a field theory, and the chain rule on the coordinate derivative of the Lagrangian density, closed by the Euler-Lagrange equations, hands you the statement that the derivative with respect to nu of t sub mu upper nu equals 0. That is 4 conserved currents indexed by the direction you translate in. Charge conservation is the template. T is that same template. T is that same template carrying a free index, so its charges are the 4 momentum. What the chapter is for in Nastasse's arc, it converts the Hamiltonian from a preferred scalar into the 0,0 slot of a covariant object. The remaining slots, energy flux, momentum density, and stress were already sitting there unnamed in continuum mechanics. This section shows how one equation, solved under successively weaker assumptions, generates the whole chapter. Maxwell plus the Lorentz force, close classical electromagnetism completely. What remains is a catalog of boundary conditions, static, uniformly moving, arbitrarily moving, each one unlocking its own named law. The generative move is that the later cases are the earlier ones seen from a different frame or at a later time. Biot-Savart is Coulomb boosted. Liénard-Wechsler is Coulomb retarded. Nastasse's closing section adds the twist that pays off downstream. With sources removed, replacing the field strength, F by its dual, star F, leaves the equations untouched. E and B are therefore one single field, seen 2 ways, and that identification is a symmetry of the theory. This section explains how Maxwell's vacuum equations, treated as an ordinary linear theory, still conceal a topological invariant. The whole chapter turns on that claim, and it lands by restricting attention to null fields. The move is to introduce a second potential, C, dual to the usual potential A. This is legitimate because the divergence of E equals 0 mirrors the divergence of B equals 0. From the 2 potentials you build 4. Chern-Simons or BF integrals, the helicities. Their time derivatives are E dot B and E squared minus B squared impose the null condition E plus IB quantity squared equals 0 and all 4 helicities freeze. A conserved quantity that arrives with no interaction and no dynamics is a topological charge waiting for its map. Here, that map is the Hopf index. The Hopfion is the field configuration, realizing index 1, electric and magnetic lines linked exactly once, the shape breathing in time while the topology stays fixed. This section explains why electromagnetism is the price of a local choice, and why charge exists at all. Gauge symmetry is a redundancy you install so that a local phase choice costs nothing. Start with a complex scalar whose Lagrangian ignores the overall phase. No other hands you a conserved current, and that current is electric charge. Charge exists because nothing physical distinguishes psi from psi multiplied by e to the I alpha. Now demand the phase be choosable independently at every point. The derivative breaks. It compares fields at neighboring points that no longer share a convention. The repair is a connection, mu, transforming exactly to cancel the mismatch. Electromagnetism drops out as the price of local arbitrariness coupled to the very current the global symmetry produced. That is the chapter's whole move. Global symmetry gives you the charge, and localizing it gives you the field that charge talks to. This section explains how a symmetry becomes a conserved quantity. A symmetry is a machine that manufactures conserved quantities, and Nastasi's chapter installs that machine in its cleanest form. Hand it a continuous global transformation, the variation of phi with upper index I, and shell with upper index I, all shell with upper index I and lower index j, acting on phi I with upper index j. Out comes the current j with upper index mu and lower index a equal to the derivative of the Lagrangian with respect to the derivative of phi a, contracted with the whole derivation is one line of integration by parts. The equations of motion kill the bulk term, leaving a total derivative that must vanish. What the chapter is for in the book's arc, it retroactively explains every conservation law already used. Translations give the stress-energy tensor, T, with upper index nu and lower index mu. U1 phase symmetry gives electric charge. Objects derived ad hoc in earlier chapters are now single instances of one construction. The generator, the current, and the charge become the same thing wearing three clothes. Q sub A represents T. Sub A on the fields acting through Poisson brackets. This section explains what a fluid actually is as a derivative expansion, and where that expansion leads once it is written covariantly. A fluid is the derivative expansion of any interacting system. Zeroth order gives the ideal fluid, continuity plus Euler, no dissipation. Each further order attaches one more derivative of the velocity field, and shear and bulk viscosity are simply the two coefficients the rotation group permits at first order. The chapter's payoff is that the same expansion, written covariantly as the vanishing divergence of the stress-energy tensor, partial sub-mu of T super mu nu equals 0, admits a null dust, a four-velocity of zero norm, U super mu U sub mu equals 0, with pressure equal to 0, with pressure equal to 0. Pure electromagnetism with F squared, that is the squared O will EQ electromagnetism with F squared, that is the square of E plus E, and ID's one such null dust. So the Hopfion imports wholesale, and the knotted solution that Kelvin's knot theory was invented to chase in 1858 arrives from Maxwell rather than from hydrodynamics. Conserved helicity is the Chern-Simons invariant that makes such knottedness possible at all. This section explains why one-dimensional statics is mechanics wearing a disguise. The static field equation, the second derivative of phi with respect to x equals the derivative of v with respect to phi, is Newton's equation for a particle sitting at position phi at time x rolling in the inverted potential minus v. Finite energy demands that the particle begin and end at rest on maxima of minus v, which are distinct vacua of v. So lambda phi to the fourth admits no kink, while the Higgs double well does, its hyperbolic tangent profile being the roll from one hilltop to the other. Stability then costs no dynamics, the endpoints are quantized, and the topological charge, Q, merely counts winding. The vacuum set fixes the arithmetic. Two minima give Q the values -1, 0, and +1. the periodic ladder of Syme, Gordon compactifies field space to the circle, and Gordon compactifies field space to the circle. This section shows why a baryon is a homotopy class. The chapter earns that identification in one move. Low energy QCD is a map U of X into SU2. SU2 is an integer winding number and integer winding number, and constancy of the field at infinity compactifies three-dimensional space, plus the point at infinity into the three-sphere as well. Every field configuration is therefore a map from the three-sphere to the three-sphere, as every field configuration is therefore a map from the three-sphere and integer winding number. That integer is b equal to -1 over 24 pi squared times the integral over three-dimensional space of the epsilon tensor, with indices I, j, k, contracted with the trace of Li times Lj times Lk. It is conserved because it is a homotopy invariant. No equation of motion is required for its conservation. The Skyr-Me term buys the scale. Its chordate commutator supplies the gradient cost that stops the winding from shrinking to a point. The Hedgehog ansatz, u equal to the exponential of I times f of r times n hat dotted into sigma, then forces f of 0 to equal n times pi. Regularity of the ansatz at the origin and integrality of the topological charge are one and the same condition. This part explains why one field theory covers magnets, superfluids, and superconductors at once, and how a single logarithm produces a phase transition. A magnet, a superfluid, and a superconductor are the same field theory wearing different clothes, a phase angle, theta living on a circle, with energy penalizing gradients. Everything follows from the periodicity because theta is identified with theta plus 2 pi. The massless scalar admits configurations no smooth deformation can undo. These are vortices, labeled by an integer winding number n, each costing an energy of pi times n squared times the stiffness j times the natural logarithm of r over a. That single logarithm is the chapter's whole engine. It competes against the vortex entropy, 2 times Boltzmann's constant, times the logarithm of r over a, which grows with the same logarithm. So the free energy switches Zine at one temperature, and the Kosterlitz-Thouless transition falls out of arithmetic rather than analysis. Nastasy's arc lands here. Topology is what makes condensed matter phases distinguishable at all. This section explains what the radiation problem asks of a field theory, and how Heisenberg turned that question into a way of selecting the theory itself. Radiation asks one question of a field theory: what does the disturbance look like right at the wavefront? The answer turns out to be a constraint on the Lagrangian, not on the source. Heisenberg's move in chapter 23 is to run that constraint backwards. He demands that an ultra-relativistic pion pancake carry a finite value of the squared gradient of phi at the shock. Both the free theory and the lambda phi to the fourth theory fail this demand. Both give phi approximately equal to a plus terms of order s, so the invariant dies as s goes to a plus terms of order s, so the invariant dies as s goes to 0. Only an action with infinitely many derivative interactions survives, and the DBI form is essentially forced. The chapter's shape is a selection principle. A boundary behavior picks the theory. This section explains why solitons cannot survive in more than one spatial dimension without gauge fields, and what that impossibility buys. A soliton in one dimension is a fact about a potential. In higher dimensions, it becomes a fact about field content. Derrick's argument is pure scaling. Rescale any static configuration so that x becomes lambda times x, and the energy splits into two terms, lambda to the power 2 minus d times the kinetic energy plus lambda to the power 2 minus d times the potential energy. Stationarity at lambda equal to 1 forces the quantity 2 minus d times the kinetic energy, 2 equal d times the potential energy. That is satisfiable only at d equal to 1, where it reproduces the virial theorem. Above one dimension, both terms must vanish. So the chapter's function in Nastassy's arc is negative first and constructive after. It closes the single scalar door and opens the gauge field, 1, staging the two-dimensional vortex, 2 chapters ahead. This section explains how the Nielsen-Olesen vortex gets its energy bound and why that bound is an integer. Complete the square in the energy, and what survives is a boundary integral. A boundary integral of a phase that must close on itself takes only integer values. That is the chapter. The energy is greater than or equal to 2 pi times n times phi 0 squared, where n counts how many times the scalar squared, where n counts how many times the scalar's phase winds around the circle at infinity and is simultaneously the quantized magnetic flux. Chapter 24 built this machinery in 1 plus 1 dimensions. Here, the bound is conditional. Saturation demands that lambda equal E squared, the BPS limit, where second-order field equations collapse to first-order ones. Abrikosov found the object first, as flux tubes in type II superconductors, before the field theory existed to name it. Electromagnetism structure survives the loss of commutativity, and the survival costs the field its passivity. Once the symmetry group is non-abelian, the connection A sub mu carries the group's own index, so the commutator of A sub mu with A sub nu no longer vanishes and joins the curvature. The curvature becomes F sub mu nu equals the partial derivative with respect to mu of A sub nu minus the partial derivative with respect to nu of A sub mu plus G times the commutator of A sub mu with A sub nu. That single surviving bracket is the chapter's whole content. The gauge field becomes charged under itself, self-interacting. The Yang-Mills equation, the covariant derivative with respect to mu of f to the mu nu equals 0, replaces the ordinary derivative with the covariant one everywhere, including where the field acts on its own strength. Everything downstream, asymptotic freedom, confinement, the gluon, is that non-commutativity cashed out. This part explains what breaks when you insist that Maxwell duality survive the addition of sources. The potential is what breaks. Once the exterior derivative of f equals k, which is non-zero, no globally defined A can exist. The repair is to define A on patches, glued across their overlap by a transition function, lambda. Magnetic charge then equals lambda's failure to close around the equator. A winding number, the first Chern number, forced to be an integer by single-valuedness of any charged field living there. Hence Q times G equals 2 pi n, one monopole, anywhere, quantizes every electric charge, everywhere. The only theoretical argument for a fact experiment already reports. The chapter's generic move, an obstruction to a global potential, becomes discrete, gluing data, and physics reads that integer as a quantum number. This section explains where the monopole's magnetic charge comes from, the topology of the fields at spatial infinity. Charge stops being a property of the field and becomes a property of a map. Finite energy forces the fields at spatial infinity into the vacuum manifold. M, the quotient of the gauge group, G, by the unbroken subgroup, H, For the Georgi-Glashow model, that quotient is a two-sphere, so the boundary data is a two-sphere, so the boundary data is a map from the sphere at infinity to that two-sphere. The homotopy class of that map, call it nu, lives in the second homotopy group of M, which for this model is the integers. That class is the magnetic charge. Written out, the magnetic charge equals 4 pi times nu divided by g. The interior never enters. The ansatz only realizes a class already fixed at infinity. Nastase states the consequence flatly: you can decide whether monopoles exist before writing any ansatz by computing the second homotopy group of the vacuum manifold. Dirac's quantization condition, singular string and all, returns here as a smooth solitonic core carrying the same integer. This section explains why the instanton exists only after Wick rotation and what it counts. Wick rotation turns the square of the Hodge star from -1 into +1, and that single sign change is what the chapter is for. Only in Euclidean signature does configuration. The instanton is that configuration leave a real self-dual configuration saturating a BPS bound, with the leftover piece, the integral of the trace of f wedge f, a topological invariant counting the third homotopy group of G, which is the integers. The instanton is that configuration. Its force is interpretive. Localized in X4, it reads as an event, the classical trajectory under the barrier between vacua of winding number n and winding number n plus 1, so its action, 8 pi squared over g squared, returns as a tunneling amplitude, e to the power minus 8 pi squared over g squared, ridiculously small at weak coupling, which is why the vacuum looks squared over g squared ridiculously. Nastase closes on the descent. Monopoles mediate vortices. Vortices mediate kinks. This section explains why every soliton in the book was found twice, once by a homotopy group and once by an ansatz, and why those two findings are one act rather than two. The topological data is always the same object, a map from a boundary sphere into the space the fields are allowed to occupy. For scalars, when the field keeps varying at infinity, that space is the vacuum manifold V, and the relevant group is pi sub d minus 1 of V. Once the field goes constant at infinity, space itself compactifies, the target is the manifold M, and the group is pi sub compactifies, the target is the manifold M, and the group is pi sub d of ntinity. Gauge fields on a sphere, s to the k, obey the same rule, read one dimension down. Two patches cover the sphere and overlap on s to the k minus 1, and the transition function that glues them must wind. So the classification is pi sub k minus 1 of the unbroken group H. Nastase's payoff is the identity, the second homotopy group of the coset space G modulo H equals the first homotopy group of H computed inside G. Read in words, the scalar winding of the T-Hooft and Polyakov monopole is the Dirac monopole number. Two counts that look like different bookkeeping are one number. The ansatz is that same symmetry statement read forward instead of backward. Impose the residual invariance the configuration is required to have, and the field collapses to a single function of the radius. This section explains two ways to build a soliton without topology, and what their existence does to the argument so far. A soliton needs a sector it cannot leave, and topology is only one way to supply. 1. Fix instead a conserved, no other charge, and minimize the energy at fixed q. The Lagrange multiplier omega enters as an internal rotation, the field being e to the I omega t times a radial profile f of r, so the lump is stationary rather than static. It exists only above a threshold, Q minimum, set by where the omega shifted potential dips below zero. Nastas's second move removes even stability. The Sphaleron sits at a mountain pass between two vacua, a saddle of the energy with exactly one downhill direction. The name comes from the Greek, asphales, ready to fall. The Chakta's place in the arc is a demotion of topological charge from necessary to merely sufficient, and a promotion of energy landscape geometry. Minima, give particles. Saddles, give barrier heights. This section explains what the moduli space is and why promoting a soliton's parameters to dynamical variables turns a field theory into a geometry. The moduli space is where a field theory stops being a field theory. Solitons with a topological charge come in continuous families. A monopole has a position, a phase, a size, and each parameter is a flat direction of the energy. Move along it and nothing costs energy. Nastas's move is to promote those parameters to time. The infinite dimensional field configuration space collapses to the finite dimensional manifold of degenerate minima. Written script M. Slow motion in the theory becomes geodesic motion on script M under the metric that the kinetic term induces. 2. Soliton scattering becomes a geodesic problem rather than a partial differential equation. The chapter's place in the arc, it is the last step, turning solitons from static solutions into dynamical objects, and the first place where a spacetime's geometry is derived from a field theory rather than assumed. This section explains the Chern-Simons term and the three physical readings it carries. In 2+1 dimensions, a kinetic term becomes available that the four-dimensional world forbids. Epsilon with upper indices, mu nu, rho, times a sub mu, times the derivative with respect to nu of a sub rho. It is built from the constant epsilon symbol rather than from a metric. Metric-free means topological, so the theory sees only global structure, and its equation of motion kills the field strength entirely, leaving pure gauge with holonomy. Nastas's whole chapter is that one term, read three ways. Read as a response action for real electromagnetism. It is the integer quantum Hall effect. The quantized level K becomes the quantized Hall conductance. Read as an emergent field composed from the electrons themselves. It attaches flux to each particle, and the Aharonov-Bohm phase that flux generates is fractional statistics, anyons. Couple the two readings through a BF term, and the fractional effect falls out, with quasi-particles carrying charge Q over R. One structure, worn as substrate, as statistics, as response. This section explains how two Lagrangians that share no term can nevertheless describe the same theory, and why the proof is mechanical rather than clever. Write a first-order master action carrying an auxiliary field beside the original. Eliminate one field by its own equation of motion, and the topologically massive theory drops out. Eliminate the other and the self. Dual theory does. The dual variable is whichever field you kept. Underneath sits one arithmetic fact. The self-duality condition, the Hodge dual of F equals m times A, squares to Proca. The product of del plus m with del minus m gives del squared minus m squared. So each sign of m carries half the modes. Everything later is that same elimination, performed at a different rank. P forms in dimension d equals 4k minus 1, and T duality inverting the 0,0 component of the metric on the worldsheet, trading weak coupling for strong. This section explains the single structural move that generates all three dualities at once. A duality is a Lagrange multiplier promoted to a field. Each construction here runs the same 3 steps. Take the action, write a master action in which the would-be derivative is an independent field constrained on shell by a multiplier. Then choose which of the two to integrate out. Kill the multiplier and the original returns. Kill the independent field and out falls the dual. Maxwell becomes Maxwell in 3+1 dimensions. The abelian Higgs phase becomes a gauge field, B mu, in 2+1 dimensions, and a phase becomes the antisymmetric field, B mu nu, in 3+1 dimensions. The rank of the multiplier is fixed by the codimension of the defect. A point vortex needs a 1 form. A vortex string needs a 2 form. No other current on one side, topological current on the other. The coupling inverts, G, becomes 1 over G. This section explains what a spinor actually is and why one of the 3 standard definitions subsumes the other 2. A spinor is a representation of the Clifford algebra. The anticommutator of gamma mu with gamma nu equals 2 times G mu nu. Nastase gives 3 definitions and ranks them. The half-integer Lorentz representation, the -1 picked up under a 2 pi rotation, and the Clifford one, which he calls our third, and most general. The ranking is the chapter. The first 2 describe symptoms in one spacetime. The third generates the object on any manifold carrying a metric, since the anticommutator is the metric. Bosons fail to be Clifford representations at all. Everything downstream follows from that one bracket. Chirality. The Dirac conjugate, Majorana reality. This section explains where the Dirac equation comes from and why its solution structure is already fixed by that origin. The Dirac equation is what you get by demanding a square root of the Klein-Gordon operator. Factor the D'Alembert minus mass squared into 2 pieces, d/-m times d/+m. That factorization works only because the anticommutator of the gamma matrices reproduces the metric. Everything else in the chapter follows from this one move. Taking the square root halves the degrees of freedom. Klein-Gordon merely restricts which momenta are allowed, whereas Dirac relates half the spinor components to the other half. So a 4-component field carries exactly 2 spin states, twice, once at positive frequency and once at negative frequency. Nastase's placement is deliberate. This is the classical field theory of a field that cannot be classical, since Pauli exclusion forbids the many particles in one state limit that makes a field classical at all. This section explains why general relativity treats coordinates as a redundancy rather than a convenience, and what that buys. Special relativity says the laws do not care which inertial observer writes them. General relativity says they do not care which coordinates at all, and the redundancy that buys is a gauge symmetry rather than a mere convenience. Take an infinitesimal shift of position, x mu becomes x mu plus x mu, and write down the resulting change in the metric, delta G mu nu. The first term is a translation. The rest has the tensor shape of a gauge variation. Delta A mu equals the partial derivative of alpha with respect to x mu. Gravity is the gauge theory of local translations. That single move fixes everything downstream. The metric G mu nu as a function of x is the gauge field. The Christoffel symbol is its connection, a kind of gauge field of gravity. And free fall is a covariant derivative set to 0. The chapter's whole job is establishing the kinematics, the dynamics weights for chapter 39. This section places gravity inside the book's gauge theory, grammar, and then demotes the action everyone treats as fundamental. Gravity enters that grammar unchanged. The connection is gamma. The Riemann tensor is its field strength, partial A minus partial A, plus the bracket of A, with A and curvature is what the commutator of two covariant derivatives measures when it acts on a vector. The recipe used for every earlier field, build the invariant and vary it, needs no amendment. It needs no amendment. A dechendral love, the d-dimensional volume element multiplied by the square root of minus the determinant of the metric. The chapter's real claim is a demotion. Einstein-Hilbert is merely the lowest dimension invariant that is not trivial. The volume alone varies to the condition that g mu nu equals 0, so the Ricci scalar R is simply the next thing up the dimension ladder. Nastasi states it flatly. There is nothing sacred about the Einstein. R squared and the Ricci tensor squared sit directly behind it, suppressed only by the Planck mass, around 10 to the 19th power giga-electron volts. This section explains how general relativity turns into an ordinary field theory once you allow only small departures from flat space. Set the metric g mu nu equal to eta mu nu plus 2 kappa n times h mu nu, and general relativity demotes to a field living on flat spacetime, expanding the Einstein-Hilbert action to quadratic rank 2 tensor. 2 tensor to quadratic order leaves the Fiers Pauli action. General covariance degenerates at the same time. Nonlinear diffeomorphism becomes the statement that the variation of h mu nu equals the partial derivative with respect to mu of xi nu, plus the partial derivative with respect to nu of xi mu. That is an ordinary gauge of gravity, thereby enters the book's catalog as spin 2, seated beside spin 1, and every spin 1 result transposes index by index. De Donde is Lorentz. The equation of motion is Klein-Gordon. 2 transverse polarizations survive. Gauge fixing. Radiation is the retarded source integral. The arrow reverses 2. The only unitary gauge invariant nonlinear completion of Fiers Pauli is the Einstein-Hilbert action itself. Geometry is what a massless spin 2 field forces. This section explains how the full nonlinear machinery of Einstein's equations reduces, under spherical symmetry alone, to a single ordinary differential equation carrying one integration constant. Symmetry consumes the coordinate freedom. You begin with 4 unknown functions of the radius r and the time t, then 2 residual coordinate changes remove 2 of them, leaving 2 survivors called nu and lambda. The vacuum equations then force lambda to equal minus nu and force the time derivative of lambda to vanish. That second condition is the interesting one. Staticity comes out as a consequence, derived from the field equations rather than imposed at the start. This is Birkhoff's theorem, arrived at on physical grounds. Newton re-enters only at the boundary, as a condition imposed as r goes to infinity, and his mass m is precisely the constant of integration. The exact solution costs no perturbation series. It costs a symmetry. What falls out is gravity's first strong field object. Its horizon sits at the radius equal to 2 times m times Newton's constant, and that horizon is a defect of the coordinates. The curvature scalar r stays perfectly finite there. A gravitational field behaves as an optical medium. The move in this chapter is to push the null geodesic in the Newtonian limit metric until it reads the time derivative of the quantity 1 min g Newton over x to 4 mg Newtonian potential times the coordinate velocity equals minus twice the spatial gradient of the Newtonian potential. That form is identical to Fermat's principle with a refractive index of 1 minus twice the Newtonian potential, so deflection reduces to Snell's law and integrates to 4 mg Newton over x. The factor 2 carries the test. special relativity plus Newtonian gravity bends light through the time-time component of the metric alone and yields 2 mg, Newton over x. General relativity's spatial curvature, the term 1 minus twice the Newtonian potential, multiplying the spatial identity, contributes an equal and independent share. Eddington's eclipse observation in 1919 was therefore an experiment that counted metric components. It is the first observable no potential theory can imitate. And that is this chapter's job in the book's gravity arc. This section explains why one family of exact gravitational wave solutions makes Einstein's equations go completely linear with no approximation anywhere. Einstein's equations become exactly linear on the right ansatz. Let the metric carry a single function, h along a null direction, the Brinkmann form of a parallel plane wave. Every curvature invariant ben where Berrier in where. Every curvature invariant then vanishes, and Ricci is left with one surviving component. The plus component equals -1/2 the transverse Laplacian of h, meaning -1/2 the sum of the second derivatives of h across the transverse directions. That is a flat space, Laplacian, and it holds exactly with no linear superposition, therefore, returns inside full general relativity, sources included. Two waves running the same way. Simply add, and so do their plus components of the stress tensor. The reason this happens is nullness. A disturbance moving at the speed of light never catches its own field, so gravity cannot gravitate here. That single property is what removes the nonlinearity, not any weakness of the field. Penrose's limit theorem then makes this sector universal rather than exotic. Focus in on any null geodesic in any background whatsoever, and the limit you obtain is a parallel plane wave in flat space. This section explains how demanding a symmetry turns Einstein's equations into solvable ones, and what the resulting space-times look like. Symmetry is the whole engine here. Demand invariance along two directions and you get a wall, along one and you get a string. In each case, Einstein's equations collapse from 10 coupled nonlinearities into a single ordinary differential equation. The chapter's real move arrives with the string. The ansatz is independent of z, with the zz component of the metric equal to 1, so gravity in 3 + 1 dimensions is secretly gravity in 2 + 1. Nastase counts degrees of freedom, d times d minus 3, all over 2, which is 0 at d equals 3. No propagating graviton. The string's field is therefore locally flat and entirely global, a cone of deficit angle 8 pi times Newton's constant times mu. Light bends by exactly that wedge because it never bent at all. Add a cosmological constant to that trivial theory and the BTZ. Black hole appears anyway. This section explains how imposing a symmetry group on space-time turns Einstein's equations into something that stops behaving like field equations at all. Homogeneity plus isotropy leaves exactly one free function, the scale factor a of t, and one discrete label k, which takes only the values 0, +1, or -1. 10 coupled partial differential equations collapse to two ordinary differential equations. Nastase builds the ansatz in stages. First, he gauges away the G0I components. Then, he absorbs f of t into proper time. Then he demands constant curvature as the invariant expression of homogeneity. That last demand is the step that does the work, because a metric can look isotropic about one point without being the same at every point. Its place in the book is the second exact solution after Schwarzschild, and both are reached the same way. The symmetry group itself is the solution method. The balloon in figure 45.1 carries the physics. Hubble recession falls out of the scale factor, A of t, directly, never postulated separately. This part explains why rewriting gravity in terms of the Vierbein makes its gauge structure visible. Change variables until gravity's gauge structure is visible. The metric conceals it. Its square root, the Vierbein E superscript, a subscript mu, splits one index into a curved one and a flat one carrying local Lorentz invariance. The spin connection, omega subscript mu, superscript AB, antisymmetric in a B, and therefore joint valued, becomes an honest SO3, 1 gauge field, whose field strength is the curvature, to form R superscript AB. The payoff lands the line later. The no torsion constraint, differentiated, gives R superscript AB wedge E subscript B equals 0. The vacuum Einstein equation turns out to be the same statement about the dualized curvature, R tilde superscript AB wedge E subscript B equals 0. So vacuum gravity is a self-duality condition. Euclidean solutions inherit the entire BPST apparatus, Iguchian-Hansen's metric, and Hawking's continued nut metric as gravitational instantons.